Okay, everyone, welcome back to CSE 373. Hope you got to enjoy your weekend off. Today, we are going to continue our journey into algorithmic analysis, but we're going to go into some different areas. Namely, we're going to start looking at how do we use these tools to analyze code that uses recursion. I want to start by talking a little bit how these videos for today are going to work. This first video is going to be some announcements and some overview, and we're also going to be doing a fair amount of recap from stuff from last week to really make sure we're all on the same page in terms of the terms and tools that we described. I'll also have some new examples and ways of thinking about these concepts in this video. So there's definitely will be some new perspectives on the stuff we covered last week. But this first video is going to mostly be reviewing and making sure we're on the same page for this stuff. So before we dive into content, I want to talk a little bit about some announcements. So do remember, CSE 373 is a tough class. There are lots of things that we are asking you to do, and it can be a little overwhelming to keep track of due dates and where resources are. Do remember that the course website has everything you need. It has all our planned due dates. It tells you when each assignment is due. You can click on any of those links. It takes you to the appropriate page. So please make sure you're checking this frequently. As a reminder, Project 1, which is a partner, which can be done in pairs or partners, is due this Wednesday at 10/14 at 11:59 p.m. I remember all times on the course websites are Seattle time. So that's Project 1 is due. Since it's a partner project, it's important that you remember how partnerships should work in this class when it comes to things like late days or turning in the assignment. So please make sure you follow the spec when it says how you turn in for you and a partner. And do remember that you are allowed to use late days on any of these assignments. But our syllabus does talk about for partner projects, turning in the project late does use a late day from both partners individually. So that's just one thing to keep in mind when you're thinking about planning your schedule. But please, those late days are for you when something doesn't go as planned. Or maybe something's taking you a little bit longer than you thought. That's what late days are for the unforeseen circumstances. Now, you do want to be a little careful not use them all on the first couple assignments, but don't be afraid to use them. The other thing that we wanted to remind you about is we released exercise 1 last week. So the exercises are more conceptual. They're small, short answer problems asking you to work through little examples. As a reminder, the exercises should be done individually. This does not mean we don't want you talking to anyone about the exercises. You should be talking with your peers about course concepts, about ideas for how to tackle these problems, but all the work you submit should be your own. So we don't want you copying or looking at or having someone read off word for word the solution to their solution to one of the problems. We want all your collaboration to be at a high level. You can see our syllabus for some suggestions on how to do that. And as a reminder, exercise 1 is due Friday, October 16th, also at 11:59 p.m. One last thing we want to remind you about, because we haven't seen too much of it yet, there's also an anonymous feedback form. So if you want to share your thoughts about the course with the course staff, you can fill this out. It will go to me. I won't know who you are. And especially, in this online world, we're extremely grateful for your insights and trying to help us shape what we're doing around best helping you. Do note, because it's anonymous, I won't be able to respond to you personally. So if it's something like a personal circumstance, I'm not going to be able to reach out to you individually because I don't know who you are if you're anonymous. But please use that if you feel like you need to. Okay. So before I dive into some review, I want to give you a chance to kind of test your understanding. So testing is a really good way to make sure that you are staying up to date with something, evaluating kind of in that metacognitive process where you are. And so tests are a great way to help you check as an external factor. So before we do any review, I want you to try this on your own. Which of the following statements are true? Select all of them that apply. Okay, so hopefully you had a chance to try this out. So it turns out that all of these statements are false. Not any of them are necessarily true. So let's walk through step by step and talk about why. A big theta bound exists for every function is not true, because if the big O and big omega disagree, if it's not upper bounded and lower bounded by the same function, then it doesn't have a big theta. So big theta is precisely defined for when big O and big omega agree, and we saw some examples of when they don't, like that is prime example, the runtime for is prime. The next one possible best case for adding to array dec is when it's empty. This is also false, because the way we define cases is you need to be thinking about things other than the input size, other than the size of your data structure. You need to allow the size of the data structure to vary whenever you think about a case. And we'll talk about that a bit more later and actually come back to this type of question. The next one, we only use big omega for worst case analysis. This is also false. We separated our pipeline of code modeling, which you can use cases of best case, worst case, other cases, and then you do asymptotic analysis, which could be big O, big omega, big theta. You could do big omega on the best case or big omega on the worst case. You could mix and match these however you want. Big omega is just about lower bounds. It doesn't matter which function you're analyzing. It just tells you that that function is lower bounded by some other function. And then this last one is if a function is big O of n squared, it can't also be big omega of n squared. This is sort of true for a lot of functions, but it's not true if the function exactly matches n squared. So the definition of big theta is if something's big theta of n squared, it has to be both big O of n squared and big omega of n squared. So when these bounds are tight, they can agree. So you do need to watch out for, you can't just say, oh, well, because it's big O, it's not going to be big omega. But when you start talking about looser bounds, when a bound is loose and saying like, oh, big O of n to the fifth upper bounds this because it's a really, really loose bound, well, it's unlikely that it's also going to be big omega of that because that's a very, very loose upper bound. It's going to be bigger than the true function. So all things to just keep in mind. But we're going to go through and actually review these concepts more explicitly, but I just wanted to give you that opportunity to kind of test yourself. So the learning objectives for today, before we go, part of it is going into be review, is after this class and coming to class and practicing, you should be able to distinguish between asymptotic analysis and case analysis and apply both to code snippets. Describe the 3 most common recursive patterns and identify whether code belongs to one of them. We'll introduce recursive patterns later. And then modeling recursive code using a recurrence relation, we'll talk about what that is, and use this thing called the master theorem to characterize a recurrence relation with big O, big theta, big omega bounds. Okay, so that's our learning objectives for today. In this video, we're going to be doing some mostly review, but introducing some new ways of thinking about this. So remember, our algorithmic analysis roadmap started off simple with just code modeling asymptotic analysis, but on Friday's lesson, we introduced choice. And now for code modeling, you now have case analysis, where you can look at different cases separately. And then once you come up with a runtime function for any case, then you can do asymptotic analysis, finding big O, big theta, big omega. And do remember, big theta might not necessarily exist. It only will exist if big O and big omega agree. Remember, and we have some formal definitions of big O and big omega and big theta. So remember, big O is an upper bound. If f is big O of g, it means g will eventually dominate f. We have that definition for all n greater than n naught. F of n is less than or equal to c times g of n. Big omega flips that around as a lower bound. If f is big omega of g, it's going to be eventually lower bounded by g. And it's basically a statement of at least. It takes at least this long run. And big thetas are kind of like equal to, meaning it's upper bounded and lower bounded by the exact same class of function. Remember, I say class of function there because we allow different constant multiples for this definition. So upper bounded by a function times one constant, lower bounded by that same function times another constant. And so this exists only when the big O and big omega agree on what they are. We'll use these terms quite frequently. So a note about asymptotic analysis tools. So for most of our examples from now on, we'll actually be asking you about big theta because it's the most specific. We normally would be saying, oh, give us big O, but make sure it's the tightest one. But for all of the functions we're going to analyze, there usually will have a big theta, and so we'll just ask you that to make sure our description can be shorter. And as another note, usually when you think about industry, people often use big O to mean tight big O without saying it. So if you're in an interview and they ask, oh, what's the runtime of this? And you say big O of n factorial, they're probably not looking for that, even though that's a true statement, because n factorial blows up really quickly. Um, and sometimes they actually really just mean big theta, but they might not know that term necessarily, or they don't know how to use it correctly. So you got to be a little bit careful. Like in industry, they use big O slightly differently. So our focus is big theta because that's kind of the most important one. And usually when you hear people in industry, when they say big O, they might actually mean big theta. So we're going to use big theta pretty much most of the time. Any simple function like a polynomial, you can use our rules to drop constants and lower order terms, and you can see what the big theta will be at a glance. But then when you have some really weird functions like is prime, where it's kind of like sometimes it's n and sometimes it's just constant time, well then since the big O and big omega don't agree, you're not going to be able to come up with the big theta. Then we also talked about cases. So this is a new slide, a picture I haven't shown you before, but I kind of hope to help you think about what we meant by a case. So remember, when we do case analysis is part of code modeling. And what is code modeling? You take code and come up with a runtime function. That means you need to come up with a function that says for any input size n, how many steps is going to take, right? And that key statement there is for any input size n, that f of n has to be defined for all n. So when we think about cases, best case, worst case, whatever case, you have to come up with things that vary about the problem other than the input size, because the input size needs to be used in order to come up with the runtime function for each case. And so you should think about cases as being orthogonal, as being in a separate direction from input size, where you can kind of imagine before we had this nice 2D picture of just f of n and n, it drew a graph. And now that we introduce cases, you kind of opened up a third dimension of different things you can choose about the problem other than input size that results in different runtime functions. So a case is considering, which case we're considering is just one dimension of this space. Choosing a case lets us take a slice of those other dimensions, n and f of n. So we're saying, oh, this is the relationship between the input size and the function, the runtime function, how many steps it takes. And you could do asymptotic analysis on each of these slices. So really think of cases as orthogonal, as separate or in a different direction than input size. And that's what I mean by a case is any variation you can come up with other than input size. You can't fix input size here. And so how do you do case analysis? How do you look at a piece of code and know which cases there are? So are there significantly different cases? Do other variables, parameters, fields affect the runtime other than the input size? For a lot of algorithms, no. For a lot of algorithms, the only thing that matters is the size of the input. For example, if you're trying to print the numbers in a list, it doesn't matter what numbers are in the list. All that matters is the input size. And so you're not going to have separate cases for that. And so you might want to try to figure out how things could change depending on the input. Think through what would happen in this if this was what was passed in, or what would happen if my data structure was in this state. Remember, all of those things you're thinking about, things that you think might change, can't include the input size n. That's the thing that you need to let free because you want to come up with a runtime function that works for any n. So some examples of things you might want to look for. Can you exit any loops early? You might return early? Are some branches, if you have if-else statements, much slower than others? And then trying to determine which inputs might cause those worst cases or different cases to happen. So determining what inputs would cause you to hit that best worst case of the code. For the most part, you'll find that code either doesn't have separate cases, it's just going to be about the same, or there's generally like a best case or a worst case input, but that's not a strict rule. You can come up with any cases you want. You just need to come up with a different runtime function for each case you decide on. So I'm going to outline a couple other cases that sometimes come up if you're just talking with someone about case analysis that we're going to give kind of a loose definition for, but it's more about intuition and kind of understanding that these things exist and you've at least heard these terms. So sometimes people talk about the overall case, which is in some sense like the cloud of all possible cases. So it's like the set of all possible runtime functions that could happen for any input. So it covers all possibilities. Now notice this is not strictly a case because you can't come up with a runtime function for this necessarily. It's kind of this cloud of a bunch of runtime functions. But people still think about this because it's kind of useful to come up with, okay, in any possible case, what's the big O, what's the big omega, what's the big theta, and it just has to be a true statement for all functions in that class. So it's usually going to end up being about the worst and the best case, because those end up being at the boundaries. So you might hear people talk about overall case. There's a pretty common one where you say, well, let's just assume X won't happen case. So if you're like, oh, if this is going to happen, this is going to be the worst case thing. But you could also just in your analysis say, well, but that's not going to actually happen. So we could assume in our analysis that the array won't need to resize. And is that assumption true or not? Probably not. It will have to resize eventually. But it is sometimes a useful case to think through if it's, for example, something that can only happen very infrequently. And you might want to say, well, this is actually the more common case. Some people talk about average case. So assuming some random input, like in the linear search when you're finding an array or value in an array, kind of assuming some distribution over the possible things I could search for or the state of that array. But there are so many complications in what average means. How do you compute what's the most likely value, or what's the probability of them searching for 4 versus 8? It's kind of a mess. So for what we're going to be talking about, we don't really talk about average cases in our course. And then sometimes this isn't a real case, but it's a useful idea. Thinking about what's going to happen in practice. So making reasonable assumptions about how the world will work, and then do worst case analysis under those assumptions. We'll see this a little bit later when we talk about hashing. And we talk about, we're going to, just in practice, we're going to assume that this bad event doesn't happen too often, because in practice, it really doesn't. So it's kind of like that assume X won't happen case, but just some people say like, oh, in practice, this doesn't ever happen. Just all things that are useful to know. So how can you tell if a best and worst case exist? Well, are there other possible models for this code? Remember, a model is a runtime function. For any input size, what are the number of steps? If n is given, are there other factors that determine the runtime? And sometimes there aren't significantly different cases. Sometimes we just want to model the code with a single function and just go straight to analysis. That's okay. But usually you might want to think about, well, are there significant differences depending on other inputs? Okay, so now I want you to kind of test your understanding again. I want you to try, in your own words, describing why we can or cannot use n equals 0 as the best case in our analysis. And I actually just talked to the item pool people, and they implemented free response, so now you're not restricted to 40 characters. So in your own words, describe why we can or cannot use n as the best case for our analysis. Okay, so let's talk a little bit about this, why we can or cannot use n equals 0 as our best case. So remember that each case needs to be a slice, a function over n. So it needs to say for any input n, what is the number of steps? The input to asymptotic analysis is a function over all n because we're concerned with growth rate, what happens as n gets really, really large. Fixing n does not work for that tool because it wouldn't let us examine the bound asymptotically. So when someone says best case, what you really should be saying in your head is best case as n grows infinitely large, not best case of all inputs including n. So we don't consider like a particular input size as a particular best case because cases need to allow for n to grow infinitely large. In our next videos, we'll kind of introduce these cases and asymptotic analysis for more recursive looking code. And so we'll be practicing these ideas over and over again.